I welcome you all to this session on time complexity. In this session, we will understand basic concept of what is time complexity of a program, and we will also understand how to compute time complexity using program step method. So what is this time complexity and why is it important? So while analyzing the performance of a program or a function, we need to address a very important question, that is the program's running time acceptable for the task? If the answer is no, then nobody is going to use the program or eventually the application. So addressing this issue is of great importance. So what is this time complexity? Time complexity is the amount of computer time required to completely execute the program. So this time complexity of a program, say P, denoted as a function of T of P, will involve compile time as well as execution time for the program. We already know that once a program is compiled, it can be executed multiple times. There is no need to recompile the program once it is compiled. So consequently, the execution time is of great concern to all of us. Determining this execution time is not an easy task because it involves a detailed knowledge of compiler's attributes. So for example, for an instance n, the execution time TP is denoted as this: CA add n, CS sub n, C1 LDAN and CST STAN. So this is an instance where multiple additions and subtractions are being done. And CA, CS, CL and CST are the constants that refer to the time required to perform the operations, and add, sub, LDA and STA are the number of additions, subtraction, loads and stores that are performed when the program is run with a characteristic instance n. So determining this execution time requires great efforts. One way to determine execution time is to use system clock to program the execution, but that will be machine dependent. To have a machine independent analysis of the execution of time, we need to consider a method which considers program steps. So program step is a single unit which can be used to analyze the execution time of a program in a machine independent characteristics. So for example, consider these two statements which can be treated as program steps. This method gives us a machine independent estimate, but we must know how to divide the program into distinct steps. The only requirement is that time required to execute each step is counted as one step, be independent of the instance characteristics. So let us see an example of a function and the program steps required for the function, which in turn can estimate the time required to execute the function. If we want to obtain the step count for a function sum, over here we have to declare a variable count. This count is declared globally with a value initialized to 0, and it is incremented at every program step. So in this example, the first program step is this assignment statement. So count is incremented by 1 over here. Inside the for loop, to check the conditions of the for loop, the count is incremented once. Again, inside the for loop, the count is incremented once for the assignment statement. When the for loop executes, it checks the condition for execution. So the count is incremented once for the last execution of the for loop. And the count is also incremented 1 for the return statement. So these are different overall 5 program steps in this function sum. If we analyze these steps, inside the for loop, there are 2 steps. Each of the steps execute n times. I repeat once again, inside the for loop, there are 2 steps. Each of the steps execute n times. So the total number of steps required by the for loop is 2n. Outside the for loop, there are 4 program steps for assignment, for the last execution of the loop, and for the return statement. So 3 program steps outside the for loop and 2n program steps inside the for loop. So total steps required by this function is 2n plus 3. I repeat, the total steps required by this function is 2m plus 3. Now let us see how to obtain the step count for the recursive function of the sum function. So this is recursive function. It has an if condition, a return statement with a recursive call inside the if statement, and a return statement at the end again. So we use the same global count function initialized to 0. Before the if condition, we increment it once because a decision is made whether to enter the if construct or to exit the if construct. So that adds up to 1 step size. So 1 value is added to the count variable over here. 1 value is added to the count inside the for loop for this return statement, and inside the if construct for the return statement, and outside the if construct we again increment it by 1 for the return statement over here. So to determine the step count for this function, we first need to figure out the step count for the boundary condition. That is, if n is equal to 0, what will be the step count? So if n equal to 0, then this will be executed. Count plus plus of the if condition will be executed, and count plus plus for the return statement will be executed. So for n equal to 0, the step size will be equal to 2. For n equal to 0, this statement and this statement are executed. Statement inside the if and the recursive calls are not executed. So there are 2 steps for n equal to 0. For the other case, when n is not equal to 0, for n is not equal to 0, these two statements are executed as normal. So we have two statements, and since there are n function calls over here, so here we have n function calls, and these are followed by one with n equal to 0. So the step count will be 2n plus 2. See, need to note down, for this n greater than 0, we have these two calls, that is this statement and this statement executed, so which will be 2 step count. Inside the if condition, this return statement will have n recursive function calls, so that is n. For each of the recursive function calls, these two statements are to be executed, so that will be 2n. So the total step count for the recursive function is 2n plus 1. Surprisingly, the recursive function actually has a lower step count than its iterative counterpart. So if we go to previous slide, the iterative function requires 2n plus 3 steps, and the recursive function requires 2n plus 2 steps. Thus, we can conclude that recursive functions or the recursive version requires less step count. So, but we need to note down that although the recursive functions has fewer steps, it typically runs more slower than the iterative versions, as its steps on average take more time than those of iterative versions. So this is a good point to note down. So this method of computing program steps gives us an overview of the execution time required by the program, and which can help us in analyzing the performance of the program. But when it comes to recursion, we must note down that recursive versions, though it requires less number of steps, the recursive calls consumes more execution time than the iterative versions. So with this, I end today's session. In next session, we will see more examples on time complexity. Thank you all.